Hello. So today I want to discuss about a problem that appeared in CMI 2021 entrance exam. It's an interesting problem about vectors. So the question says we have two distinct non-zero vectors v1 and v2 in three dimensions, I mean R3. Now we define a sequence vn of vectors by vn plus 2 equal to vn cross vn plus 1. So in the sequence of vectors, any term is determined by the cross product of its previous two terms. We define the set S by the set of all these vectors, like S equal to Vn such that n is a natural number, and U is the set of all unit vectors corresponding to the sequence, like U equal to Vn by mod Vn, and we vary n over all natural numbers. So now I have to determine the initial vectors such that their exit vectors v1 and v2 such that cardinality of S is exactly 2. Whether exact cardinality of S is exactly 2 or 3 or 4, like does that hold or not, we have to determine that. And we have to determine if for some v1 v2, if the set is infinite, S is infinite, then whether U is infinite also or not. If the set of distinct terms of the sequence is infinite, whether we have to determine whether the corresponding sequence of unit vectors is also infinite or not. So let's do this.
This video is sponsored by Chinta.com. Since 2010, Chinta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
For part A, we have v1 not equal to v2 and both of them are non-zero. This is important. Now what is about cross product of vectors in R3? We have two vectors v1 and v2, wherever it then doesn't matter. What is v1 cross v2? v1 cross v2 lies on the plane orthogonal, direction of v1 cross v2 is orthogonal to the plane determined by v1 and v2. So wherever v1 and v2, they determine a plane. It's a two-dimensional plane. And v1 cross v2 just lies orthogonal to it. Like it can be in this direction or in this direction. This is v1 cross v2's directions. So v1 cross v2 can never be equal to v1 or v2, either except possibility that one of v1 and v2 is 0. But here we are given that v1 and v2 both of them are non-zero, so that doesn't occur. So v1 cross v2, this is not equal to v1 and this is not equal to v2, so this is a distinct term. Like it can be 0 also, but 0 is not equal to v1 and v2. So in either cases we get three distinct terms of the sequence v1, v2 and v3, that is equal to v1 cross v2. Because v1 cross v2 is not equal to v1 and v2 and it can be 0 also, and that is not a problem because 0 is neither of v1 and v2. So we get cardinality of S is at least 3 because these three are distinct terms. So the part A, it is false because we get three distinct terms. At least three distinct terms. Now we have to determine v and v2 such that exactly there are three distinct terms. So let's see. One an easy example, like you take the usual vectors 1 0 0, 0 1 0 and 0 0 1, what we define by I cap, j cap and k cap. We will use these vectors. So we define v1 to be I am just not writing the caps, v2 to be j, then v3 equal to I cross j k, v4 equal to vn cross vn plus 1 cross v4 equal to v2 cross v3, that is j cross k, that is I, v5 equal to v3 cross v4, k cross I equal to j and so on. So the sequence goes like I, j, k, and so on. Because I cross j is k, j cross k is I, k cross I is j. And it's in cyclic order, like the cycle repeats. ijk, ijk, ijk. In this pattern the sequence proceeds. So we have exactly 3 distinct terms. So this is possible. Sorry. This is possible. This is false. This is true. And you can also define in another way. Like you can take any two V1 and V2 such that V1 cross V2 is 0. Like when two cross product of two vectors is 0 when they are parallel. So you can define any V1 to be initial non-vector and you define V2 to be parallel to V1, like V2 equal to 2V1. In that case, V3 equal to V1 cross V2, that is V1 cross 2V1, that is 0. And afterwards, V4 equal to V2 cross V3, that is cross product of any vector with 0 vector is 0. V5 also like cross product of V5 equal to V3 cross V4 and cross product of 0 vectors, that is 0. So my sequence becomes V1, 2V1, then 0, 0, 0, 0, dot, 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 dot. So distinct terms are only V1, 2V1 and 0. This is also a possible case for part B, sorry. Now for part C, you have to check their vectors V1 and V2 such that the cardinality of S is exactly 4. For the previous parts, we used I cap and J cap. Now just use a bit different thing, but similar idea. We use V1 to be I plus J and now take V2 to be J. So that the sequence terminates, but it terminates after one point. Like as I define I plus J, it will take more extra one step. So V3 equal to V1 cross V2. So I plus J cross J. That is K. Now V4 is V2 cross V3 equal to J cross K equal to I. And the cycle repeats, like V5 equal to K cross I, that is J. So how does the sequence look? V1 is I plus J, V2 is J, V3 is K, V4 is I, this is J, and V6 will be again K. So the previous my sequence was repeating like IJK, IJK. Here I just change my initial to I plus J so that it repeats, but I have one more extra term as an initial so that I get extra one term so that my cardinality of S becomes 4. So it repeats as JKI, JKI, JKI in this form. Like after I plus J, this 3-part repeats as a 3 cycles. So I have exactly 4 distinct terms, I plus IJ, K and I plus J. So part C is also true. We can choose V1 and V2 such that S has exactly 4 distinct elements. Now for some V1 and V2 S is infinite, does that mean that U must be also infinite? Well, we see that it is not the case, because try to imagine you have a sequence that is determined by I, J and K, like multiples of I and J and K, like I have I, 2J, 2 square K, 3 square, like some 2 cube J, 2 to the power 5I in this form, like all are like instead of 2 I can take 3 also, like these are multiples of 3. Anyway, like I want like these sequences are like multiples of I, J and K and determined in an usual way, but so you can see that like the scalar part is an increasing sequence. So like modulus is increasing, like here is modulus 1, here is 3, here 3 squared, here 3 cube, here 3 to the power 5. So this is strictly increasing. So as the modulus of vectors is strictly increasing, the sequence has infinitely many terms. Because all vectors have different modulus, so now no two of them can be equal. But can you see the corresponding sequence of unit vectors? Because all unit vectors are generated by I, J and K. So this corresponding unit vector is I, this is J, this is K. Like nothing is outside of I, J and K. So this sequence is like the corresponding set U, like set of corresponding unit vectors is just I, J and K, because my S set is determined by all multiples of it, and as multiples like scalar parts are strictly increasing, so that vectors are also strictly different, but their generating parts, like those unit vectors that generate that sequence, they are same, like the generators are same. that are ij and k. So even if S is infinite, you can always be finite. Like, it's not always finite, but it can be finite in a lot of situations. So my concrete example is take V1 to be I cap, V2 to be 2j cap. Now see what happens. V3 equal to I cross 2j, that is 2 into I cross j 2k. V4 equal to V2 cross V3. So 2 square into j cross k I, 2 square times I. V5 equal to V3 cross V4, that is 2 cube times j. V6 equal to V4 cross V5, that is 2 to the power 5 times j cross I is k. So like I, 2j, I, 2j, 2k, 2 square I, 2 cube j, 2 to the power 5k. Now in the next term the power should be 2 to the power 8, then 2 to the power 13. Like it's an AGP, like arithmetic geometric progression. Like the powers of 2 are in that way. So you can see that like this has only generators I, j and k, like the set of unit vectors. So even S is infinite, but my mod of U is just 3, it is finite. So in this case, my D cannot be true, like D is false. So we are done. We have first and last statement are false, but second and third statements are true, and we are done. The problem ends here.
Chinta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Chinta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Chinta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit chinta.com.